informally, because that's the way I do it. I'm going to talk about is the size of the universe. Well, when we say something is astronomical, we think it's very, very big. We're going to talk about how big that very, very big is. Now, start with, I can't fit even the moon into this classroom. So you see this, it's not a car, it's a model of a car. I could use it to describe some things, but not other things. For instance, I could tell an alien how I got here with it, but I couldn't tell him how it works because there's no real engine in this one. That's the same thing with the models. I'm going to be using models and analogies all through this because there's no way we can actually go out and see it. I'm going to start first off with a little bit of a personal story. A lot of years ago, there was a special television program. I remember I went to my father's house, my brothers came in, and we all sat around and watched this thing till about 2 in the morning. It was a reality show. There were a couple of guys trying to land a craft. They almost crashed. If they crashed, they would have died, without a question. And so I want to show you just the end of it. The television quality back then was terrible, but this was worse than normal television quality.
One small step for man, one giant leap for mankind. Oh, that looks beautiful from here, Neil. It has a stark beauty all its own. It's like much of the high desert of the United States. It's different, but it's very pretty out here.
Every precious minute of their 2.5 hours on the surface was programmed. Rock and soil samples were to be collected, photographs taken, experiments set up to catch unfiltered particles from the sun, to record moonquakes, to measure precisely by laser beam reflection the exact distance between moon and Earth.
Columbia, this is Houston, AOS, over. Houston, Columbia, on the high gain, over. Roger, the EVA is progressing beautifully. They're setting up the flag now. I guess you're about the only person around that doesn't have TV coverage of the scene.
So, obviously, that was a great accomplishment, but I don't think a lot of people understood how difficult that was. Let's first look at a true picture of the scale of the Earth and the Moon. See how far the Moon is. If it's 30 Earth diameters away. This is a model of it. I have a 1-inch Earth here, 1/4-inch Moon, which is correct, and they're 30 inches apart. This is a pretty accurate model of the Earth-Moon system. In between here, nothing. We certainly hope there's nothing.
10,000
It's
centimeters.
Yeah. Now, I want to take something about the moon and get it cleared up now. Ever notice how the moon looks gigantic on the horizon and looks kind of small up in the sky? Fact is, that's an optical illusion. The moon is no bigger on the horizon than it is in the middle of the sky. As a matter of fact, you can tell it if you hold your hand out, your little finger up, your arm at arm's length. It will be twice the width of the moon. You don't believe me? Go out and look at the moon. And if you don't believe that that's an illusion, both those moons are exactly the same size. That little toy moon on the tracks. And I can prove it. I just took the background away. See, it's easy. But if I put the background back, Again, it looks like the moon on the horizon is very big, and the moon on the tracks is very small. That's what I mean by an optical illusion. Okay, I want to, very briefly, I'm sure all you guys, because you're astronomers, understand this, but just make sure we're all on the right page. There's the solar system, which is part of the galaxy. And the galaxy is a tiny piece of the universe. The solar system is a tiny piece of the galaxy. The galaxy is a tiny piece of the universe. So we're going to start by talking about the solar system. First off, the size of the planets. Earth, Venus, Mars, Mercury, Pluto, the rocky planets. Earth looks pretty good there. Pretty solid. But if I compare them to the four gas planets, well, Earth doesn't look all that good. Now if I compare the whole thing to the sun, Earth looks terrible. It's a tiny, tiny little dot right here. Earth compared to the sun. Now, I want to do an exercise called the pocket solar system. That's why I had you get these tapes. This is kind of fun. And what it does is it doesn't show you how far between planets, but it shows you the ratio of the distances. So what I want you to do, take one of these tapes and write on one end of it, the sun, and on the other end of it, Pluto. You see why I asked you this. And then we're going to place all these parts. Okay, has everybody got the sun and Pluto? One end the sun, the other end the Pluto. They're pretty big, but you'll see why they're pretty big. You done this, Ken? You done this? No, it's kind of fun.
But I get an idea. It's okay.
Yeah. Okay. Now you take the Pluto and the sun, put them together, and fold the tape in half. Unfold it, crease it, and I'm afraid these tapes hit a little crease, but on that middle, good idea to draw a line. Like Uranus.
In the middle?
Wow. That's already a little surprising, that Uranus is in the middle between the sun and and Pluto. Okay, everybody got Uranus in place? No?
I'm full. You picked the wrong guy for full. Sorry. We're gonna need another 15 or 20 minutes.
Maybe you'll need it.
Okay. Sorry, must be
Okay, next step is take the fold that has Uranus in it and put it up to where the sun and Pluto is.
Yeah.
Fold it once and twice, so you're down to only a quarter. Right? And make a real sharp crease And then we're gonna unfold it. So halfway between Uranus and Pluto is, of course, Neptune. What? Neptune. Half between Uranus and the Sun is Saturn.
Hold on a second. Halfway between,
Now, here's where we are. We're gonna,
halfway between,
well, let's look at that. I got a lot of planets to put in here.
Pluto and
There's the sun.
So I should have more things filled out. Hey, and I know sometimes it gets confusing, but, okay. Take the sun, fold it up to Saturn, unfold it, and put a line, and that's Jupiter.
no, no, wait a minute.
So we're at folding from the sun to Uranus, right? And then we get Saturn?
Yeah.
Yeah,
Yep,
but
and then
then,
Jupiter was there.
And then Jupiter is the next one after you fold from the sun.
Halfway between
Yeah,
Saturn
sun to
and
Saturn.
the Sun.
So the sun to Saturn.
greater than the sun. Greater than the sun.
Now,
That is Jupiter.
don't get ahead in this step.
Yep, so right in that.
Fold the Sun and
Yeah,
up
okay, so,
to
yeah, that's right.
Jupiter, make a crease,
oh, I'm thinking right.
and put asteroids in there.
No, it's Jupiter's closer to the sun than Saturn.
Okay,
Oh, wait, it's not. I'm the back part.
right.
If you do it wrong, the planets aren't gonna move.
I don't know about that.
You fold the Sun up to Jupiter,
So now, if you do the sun to Jupiter, fold that.
Is that what you said?
That'll get you to where.
well, we're doing pretty good, we've only got 4 planets to go. In this. Well, we're gonna fold the Sun up to the asteroids,
That's Mars.
unfold it, and write Mars in it. Now I got 3 to go. In this much of the solar system. Okay, if you're with me with Mars,
And then he's not even important.
fold the Sun to Mars, then fold that fold up to Mars, like this. 2 folds. When you unfold it, you'll see you've got 3 creases. Those 3 creases are, of course, the Earth, Venus, and Mercury. So, a lot of people find this a little surprising. We're this close to the sun compared to all that.
Makes it amazing that we got a spaceship out to Pluto. Makes the horizon.
Okay, you
spaceship.
don't like Pluto, right, Kuiper Belt?
Yeah, no, I'm saying, but we got a spaceship to go visit Pluto. It's amazing that we traveled it that
You see why
far.
it took them years to get there?
Yeah.
10 years.
This is a cute exercise, it sort of moves.
Yeah, I'm sorry, I missed some of that. Could you summarize, here's that development, could you please summarize the drawing?
You fold the sun up to Mars. And then you fold the crease back, fold the crease up. And that will make three, fold the sun to Mars. Now fold it, take the fold and fold that up to Mars. No, take the crease and fold that up to Mars. Okay, now you can fold it. Now you've got the three inner planets. Okay, that's. Now, to talk about the real distances, this handout helps a lot. It says scale distances. They will tell you the distance if the sun had a diameter of 1 meter, like this meter stick. Sun had a diameter of 1 meter, the distance is. And if, in that case, Earth would be this size to a 1 meter sun. And it would be 120 yards. A football field, then some, away from here. So you have to go a long ways. Or on this little model I have with this small sun, where's Earth? Here's Earth. Earth would be 121 feet away. This Earth that you barely see wouldn't be in this room. This Earth would be 120 feet. The planets are tiny specks in a vast ocean of nothing. Okay. Now, problem is, a lot of people see this kind of illustration in their astronomy science books. It's terrible. The proportions, Earth is 1/10 the size of Jupiter. It's about a quarter. They're all so sparse together that in no time gravity would throw them all into the sun. They couldn't possibly be that close to the sun and survive. And besides, they don't have any nebula in the middle of our solar system. But that's a typical thing you'll see. So I want to talk a little bit about terminology. Astronomical unit. We'll talk about that we talk about distances in the solar system. Astronomical unit is simply the distance, the average distance between the Earth and the sun. Nothing complicated about it. 92 million some odd miles, and it's good for measuring distances in the solar system. As an example, Mars is 1.5, Uranus is 19, almost 20 astronomical units, 20 times further from the sun than we are. Neptune is 30 times further from the sun than we are. So they're a handy measure. Another way to look at it is take a Boeing 747, traveling at 550 miles an hour, which is a reasonable cruise speed. Travel from San Francisco to New York will take about 6 hours. If I wanted to go to the sun, I'd say all the way around the world, will take us about 2 days, a little less than 2 days, assuming we don't stop for fuel or food or anything silly like that. And if we don't stop, we would get to the sun in only 18 years at that speed. If we turned around from the sun and went to Pluto, it would take us 700 years to get to Pluto. And this is the fastest any of us, most of us ever moved. In the jet airplane. That's how far apart all these little tiny spots are. Why aren't you reacting to me? My computer's not working right. No.
Not advancing?
Give me a second.
There you go.
Now I should go someplace.
There we go.
And further than I want to go. Well, a realistic view of the solar system is something like this. Now, when I talked about my 1 meter sun and how far away the Earth was, more than I thought I'd just show you from here with a 1 meter sun where the planets would be. The planet orbits would be. So if we were right here and had a 1 meter sun, now once in a while Mosen asked me to put up a model of the solar system. I told him I can't get past Mars. The reason is because Jupiter would not be on the campus. So we only do the inner planets. We do it along the walkway up there. It's kind of fun. Okay, I'm going to do something briefly about time, and then we'll move on. We look at Earth's timeline, in case you guys are feeling like you're important. Look at Earth's timeline. You put your arms out like that, whereas this is the beginning of the Earth, and here is right now. Okay, first life was right about here. First multicellular life, right about here. Wow, for a long time we were single cell. The first animals, about here. The first land animals, about here. Dinosaurs would be right up here. First humans would just be the tip of my finger. And all of civilization could be wiped out with the stroke of the nail file. That's just in case you think we're very, very important. Okay. Now, I'm going to be saying a billion a lot, so let's play with that. How big is a billion? Let's say you're very lucky and the rich uncle gives you $1 billion, but he says you can only have $10,000 a day. He doesn't want you running out buying guns.
That's tough.
You got to save up for a little bit. How long will it take? Will that trust take longer than your lifetime to give you $1 billion or less? The answer is, it would take 278 years at $10,000 a day to get to $1 billion. And in 24 hours, 7 days a week. 7 days a week, 365 days a year.
That's it.
So, $1 billion is a very big number. Okay, but that's our solar system. We'll step forward now into our galaxy. It's a pretty picture of it. Obviously, it is not a photograph. We have not gotten any spacecraft anywhere near that far away from our galaxy. We couldn't have in the time humans have been on Earth. Galaxy is the Milky Way. It's that beautiful strike of stars, and what you're doing there is you're looking at the side of it. A very good model for a galaxy is a CD. This is about the right width and the right depth, except it's a little bulgy in the center. But outside that, that makes a very good model of a galaxy, width versus diameter. So, okay, I'm not going to spend much time on this. You guys all understand it. Light year is a measure of distance, not time. It has nothing to do with time. It's how far light travels in a year. It will go, light goes around the world about 7 times in a second. Now figure how far it's going 70 times the number of seconds in a year. It's a big number. And it's equal to 63,000 AUs, 63,000 times the distance between the Earth and the Sun.
Yeah, distance, yeah. Light year.
So it's a big number. Also, another thing is a parasec. You'll hear it once in a while. It's a very handy measurement for some of the early astronomers. It's basically the distance for an object to have a movement. Yeah.
It's parsec without the A.
Oh, parsec. I'm sorry. I put an A in A. Parsec. It's basically the distance that an object would move 1 second, the parallax of 1 second, 1/60th of a degree on when you move 1 AU. It's an easy thing to measure by telescopes, but not particularly useful for much else. Thank you, I'll fix it. Okay. Let's go in. We're going to look at the universe, at the galaxy a little bit and some of the suns. This is our sun. And if we look at it compared to some of our friendly objects we look at at night, Pollux, Arcturus, Rigel, Aldebaran, Betelgeuse, and Antares. Yeah. We aren't very big. As a matter of fact, somebody tells you that all those stars are suns just like our sun. That's not true. Just about everything you see in the sky are stars much bigger than our sun. Isn't that most stars are bigger than our sun, but the only ones, because of the distance, the only ones you see are ones that are bigger than our sun.
Quick question.
Yeah.
Where is sun? I guess it's not pictured in here, right?
Well, the problem is the sun is too small.
So it's smaller than Sirius?
Yeah, it's a lot smaller than
We
Sirius.
lost it because it became,
Alright, so that's not pictured.
here's Arcturus. Okay, here's the sun.
Okay.
See how big Arcturus is there? And Arcturus is this little small thing here. So the sun doesn't even get a pixel in this picture. All right. How far apart are the stars? Well, let's say the sun was the size of a golf ball. Next nearest star, wait, here's the still is. Proxima Centauri would be another golf ball 770 miles away. Or, another way to put it, in Vancouver, Canada. It's the distance between stars. A lot of nothing in space. I can imagine holding this up in Vancouver and expecting somebody in San Francisco to see it. No matter how bright I make it. So, there's vast distances between stars. When galaxies collide, stars don't. For the most part, because there's just too much space between them. They just pass between each other. And I think I just dropped the golf ball. Yeah, okay.
It's a falling star.
Okay. Now, how many stars are in a galaxy? Well, that's easy. 400 billion stars is currently what we think. And here's how we know. Some poor astronomers out there counted them.
No. Sorry. He would have died before he got even.
Yeah.
You would.
Besides, how do you put a check mark next to them?
Yeah, that's even more time.
Yeah, 'cause they keep moving.
Well, in this jar, I've got 32,000 birdseed. How do I know? Well, I did not put them on a table and count them. What I did is, I took about 1/8 of a cup and put it on a table and counted them. And I know there's about 2 cups of birdseed in here, and I just multiply. That's the way we estimate the number of stars, not like somebody counted it. So a way to envision it is, imagine a football field. We build an 8-foot wall around it, and we fill the field with birdseed, like that. With an 8-foot wall around the whole field, take this stuff and fill the field with it. That would be about 400 billion birdseed, or about as many stars are in the galaxy. It's a pretty good analogy. You've got feelings, some are bigger, some are smaller.
Aren't there areas in the galaxy that have greater star density than other areas in the galaxy?
What?
Aren't there areas in the galaxy that have greater star density than other areas?
Oh yeah, well that's the way they count it. I mean, they look at the clusters and the various things like that. And it's not an easy count. It's not like I just take a random part of the galaxy.
So there is some logic in the way they choose different areas in the galaxy
Oh sure.
to look at the density?
Yeah, and how many of those areas are, and of course a lot of the galaxy we can't see. So we have to estimate what's
So
there.
this 400 billion really is kind of fantasy.
When I started this presentation, it said 400, it said 200 billion. I mean, it's the current best guess. But you're right, it's a guess.
Okay.
But it's something in that ballpark. It might be 10 billion, it might be a trillion, it might be 100 billion. It's really hard to know totally. You're right.
Especially since you can't see much of the galaxy.
Yeah, right.
Okay.
And as our telescopes and our equipment get better, our estimates get better. That's why in the very first time he did this presentation, it was 200. But we got better and better telescopes. We got infrared, which can see through the dust so that we can see more stars to count. And so we've been able to use, as our technology gets better, we've been able to make better and better estimates. One of the things when you do a scientific research paper, there's a fudge factor here they call it a sigma, and that is how accurate we believe this data is, because there's no way to be, this is exactly 150. That just doesn't, you can't do that in astronomy. But you can narrow it down with all these different accuracies and different types of measurements and cross-related these messages to get that number down to like a very plus or minus a very small number. So as our equipment gets better, our estimates are getting better, and our accuracy of what these counts are getting better and better and better.
We also know the structure of the galaxy by looking at the structure of the galaxies and assume it's about the same.
Yep. Yeah.
I
So these are really...
I sincerely doubt that the percentage or the accuracy is anywhere near 50%, even with your current technology.
And maybe
it could be, but we, like I said, we can compare it to other galaxies where we can actually see the whole galaxy and be able to get these data. This is what the astronomers spend all their time doing, is figuring out the best way to calculate. So a lot of these things are way better than random guess of what you think's in a jar. They're done.
They are wags, but they are.
But they are definitely, it's not 100% that is the number, because you can't do that. And most of all of our science, you'll see plots made and they show it in bars, because these bars are like, well, this is what we measured, but there's this much variation in that measurement that it is. And so all the science is done with how much this variation is, and then how we can shrink that variation down to smaller and smaller numbers. In fact, there was a recent article about the crisis in cosmology where the JWST just originally made it worse, because with their measurements, they made these two different measurement numbers farther apart than they've ever been, instead of bringing them together like we thought. So as we get better and better data, science is not this is how it is, it'll always be this way, unless it's a mathematical formula. When you're doing these other sites, it's like, this is how we can calculate the best right now, and 10 years we might be able to calculate it better, and in 10 more years, so it's always getting better.
We're certainly not going to settle it tonight.
But building telescopes with greater accuracy and having the web being able to see through a lot of dust, that will really help to narrow down the numbers. So the dust, because we're in a dust plane, and you can't see, as you mentioned, on the other side of our galaxy, this is where we are. If we're above or below, we could, or right in the plane of the galaxy. All that dust is there. But you have radio telescopes, you have infrared that can penetrate that dust and see what's there.
Yep. Yeah, so we don't have to do everything in optical light. We can go around objects with these other light.
Okay. How big's a galaxy?
I was just real big.
If we take the sun to Pluto and make it the size of a quarter, our galaxy would be the size of North America on that scale. So here's our solar system, and the galaxy is North America. So we aren't real important here, are we? Okay. Let's talk a little bit about the universe. This is more fun. I said, is this the intro? No. Here it is. This is a good model of the galaxy. If I had the galaxy shrunk down to here, next nearest galaxy is Andromeda. They'd be 8 feet apart, twice as far as I'm holding them now, roughly. Yeah.
Which is kind of actually remarkably small, given the size of these things.
Yeah.
compared to, say, the planets.
Well, we're gonna collide anyhow.
Yeah, we're in about 5 point something
So-
billion
Distance is 2.3 million light years or so. And sometimes I like 2.5. And we will collide with it. Because we're hurtling toward them at 245,000 miles an hour. Our galaxies are joining together. It will take about 4 billion years for us to collide. I wouldn't worry about it. By then, the sun would have burned up the Earth.
Yes.
Is each galaxy
Because the
moving
sun's
towards
going to
one
be
another,
red
or is
giant.
one moving towards one?
What?
Is each galaxy moving towards each other, or is there one galaxy accelerating to the other?
There is no absolute
So we don't know.
space. There's only relative motion. There's no absolute motion. There's no absolute framework. I could say relative to the universe as a whole, yes, both of them are moving because we're both attracting each other. It isn't that one is standing still and we're Andromeda Galaxy is about twice as big as ours is standing still or going toward it. We're both moving toward each other.
I prefer to think of it that we're coming after Andromeda.
Huh?
I prefer to think of it that we're coming after Andromeda.
Then only the strong thought survive.
And of course, like I said earlier, most stars won't collide.
But isn't
So,
isn't the universe
this
expanding?
is a simulation of what's going to happen with the years. You can see down here, it shows you a number of billions of years.
What?
Well, I hope I have the mortgage paid.
Why bother?
But like I said, the stars will just pass through each other. There's so much space.
Yeah, well,
The
most of
only
the stars
some
will
will
not-
get flung
will
out
not
through the
collide.
gravitational.
They will affect each other gravitationally.
But yeah, we won't be
Probably
smacking
with
suns.
planets away from stars, put other planets near stars. Don't know everything they'll do.
But the black holes at the centers of both of them will merge together.
Yeah.
And eventually, they're going to merge into a big elliptical. I could choose there.
It's going to happen to the black
Okay, on
holes
that
and-
same-
Oops.
That same thing, just to give you an idea how far apart our CD galaxies would be. Pinwheel would be about 8 feet, Bode's galaxy about 16 yards, Whirlpool about 50 yards, Sombrero galaxy about 67 yards, just as an example.
Isn't M33, you mean triangular?
What's that?
Isn't M33 triangular?
It is.
Yeah.
F51 is the whirlpool.
Yeah. So you got some, just got the type of, no big deal.
Question,
Over here.
since I don't have the patience to wait a couple billion years, do we have the ability to see any galaxies that are colliding right now?
Yeah.
Can we see galaxies that are
There's one right here, Whirlpool is one of my favorites. There are two galaxies
I
colliding.
don't have the patience for 2 billion years, but can we see through the telescope or some other means galaxies colliding? right now?
Yeah, so
Galaxy out of
the Whirlpool galaxy is two galaxies colliding. One of my
The
favorite.
Whirlpool is the most fun.
Yeah,
I really
it's
like
close. So one of my favorite things to look at and study are colliding galaxies.
Yes.
And so you can see them all the time in all sorts of different stages of all sorts of different acts. Some where they've really distorted the shape of each other. Some where they're just starting to touch. This is what I look at all the time.
These are photographs.
So we don't have to have simulations.
No. We can see it. Like the thing you need a simulation for is because you're not going to see them collide and look at it next day and see a difference because it takes billions of years for them to actually merge. But you can see if you do a giant survey across all the different areas where these are happening, you can see the different stages of the collisions. And that's how we built our models to do the simulations.
Understandable, okay,
Now,
thank you.
one of the harder questions is, how many galaxies are there? The answer is we really don't know, but we have an estimate. Basically, we'd have to build the wall around that football stadium about high.
I have a question.
Yeah.
On the previous slide showing the 3 and 4 galaxies in the order of multiple yards apart, were those galaxies and would be the size of, what would be the size of that scale?
The
Spatial
CDs.
dimension.
The CDs.
CD size.
Okay,
Yeah. He was
Yeah,
talking
that
CDs.
distance was that they were CD size.
okay.
We got a question over here.
Question?
Yeah.
Yeah, so is the word universe referring to the observable universe, which is 95 billion light years long?
What's it?
I said, is the word universe in that sentence referring to the observable universe or the entire universe?
The observable.
This is our current estimate of how many galaxies in the universe.
Right, so we can only do our estimates off of the
And on
observable.
visible universe as opposed to the total universe. That's what we think now is in the total universe. Of course, some of it we can't see and we'll never be able to see. Because space is expanding.
Exponentially.
Yeah, faster than the light can get to us.
Yeah. Yeah, well, space can expand faster than light.
Yep.
Okay, one other little thing to talk about, how fast you're moving when you're sitting still. Well, Earth rotation is moving is about 1,000 miles an hour. If the Earth were to stop, we would slam into the wall over there at about the speed of a high-speed rifle bullet. Splat. Except the wall would probably fall over and everything else. It would be a real mess. But we're moving at about 1,000 miles an hour.
That's why it's hard to keep those objects in your telescope.
Earth's orbital motion, Yeah, Earth's orbital motion is about 66,000 miles an hour going around the sun. Sun orbits the Milky Way in about 225 million miles. So that would work out to a speed of about 483,000 miles an hour. And relative to the universe, remember, all speeds are relative. There's no standing still. Nothing is the background that's not moving. Relative to the universe, our galaxy is moving about 1,300,000 miles per hour. So, what have we seen? There's that. Well, we have the Hubble Deep Field in '95, the Hubble Ultra Deep Field in 212, and the James Webb this year. And we've all used these to look deeper and deeper and deeper, and closer and closer and closer to the beginning of the universe. Now, you want to really hurt your head? It doesn't matter where we point the telescope, we're looking toward the Big Bang. In any direction. The Hubble Ultra Deep Field looked like this. Outside the deep field, this is the ultra deep field, which showed more. Now, I like this picture particularly. This is the difference between the Hubble Ultra Deep Field and the exactly same spot in the sky with the Webb telescope. Notice how much more detail you're seeing, and you're seeing things like that that are completely invisible in the Hubble Ultra Deep Field. That's why everybody was so excited about the James Webb telescope. Okay, here I'm going to have some fun.
And so the JWST image, is that all visible or is that combined, I guess?
What's that?
The JWST image, that's all visible light? Is that?
It's infrared.
Yeah.
The JUST doesn't do much
Oh, it's
visibility.
visible.
Yeah, that's why we can see farther, because as the universe expands, it stretches the light and it turns all our visible light into infrared. So you can't see faraway objects unless you're looking in infrared. And it has multiple wavelengths of infrared, so that we can see farther and farther back. So Hubble's is mostly visible light with a little bit of infrared, and Hubble's opposite. It's super infrared and medium infrared and just a little bit of visible light. And so we can see much farther objects.
Yeah.
Thanks.
Question
And
for-
what they do when you see the pictures, they bring it back into our visible space.
Yeah.
Then you couldn't see it, what they're seeing.
Yeah, there's an easily mathematical shift just to bring it into our scale.
One
Is-
question?
Question, since you're saying visible is turning to infrared, is that because of a Doppler shift? Or some?
It is essentially like Doppler
Cosmological
shift.
redshift,
Yeah,
not the Doppler shift. It's cosmological redshift.
yeah, because the Doppler shift is about sound, but it's the same principle.
equivalent of it.
It's the equivalent, yeah.
Okay.
Another question?
Yeah.
You mentioned mapping the true infrared light that's detected back into the visible space to make that picture. That has no relation to what the visible light was umpteen million years ago.
So
Did you
it is
understand
a
what I'm
little
saying?
bit of a choice, but they're trying to do it as accurate as possible. So again, some of this stuff is going to be shifted more. So when you look at this, you see more galaxies that are still very red. So what they do, so you've got RGB in the visible light. Let's just try to make this short. And each one of those has different wavelengths. Well, all that's true in the red wavelengths as well. So they make the shorter ones more like the blue and the medium ones. So they sort of just shift it all into where it would be. And so it's relatively that, but there's a tiny bit of fudge factor here and there. And sometimes we do it differently to just be able to pronounce more details in certain ways. So a lot of times, some images like this one, they're done to be looking pretty, and other times they make the shifts differently to bring out certain details that they're looking for that experiment.
But there's no relationship between the true colors at the instant the light was emitted millions of years ago and the colors we see there.
Well, it's a bit of a guess, but yeah. So there's no guarantee that this is but you do see the ones that are farther away are red, because they've been stretched more and those haven't been shifted as much. So the ones that are closer to us are more correct of the light they left than say the last ones, because a lot of the farther ones are still just showing up red because they're still stretched so far.
And you also see a lot of these. Those are gravity lensing. The gravity is something in front of them, distorting the galaxy behind it.
It's the dark matter that's actually causing that to be
Yeah.
done like that. It's gravitational lensing.
Yeah.
he said.
Yeah, so it's all gravitational lensing. We can actually reconstruct those galaxies that are back there.
Question?
Yeah.
When we talk about the universe exponentially expanding, and
Yes.
maybe I'm going to sound very dumb, is it possible at one time it was actually contracting? It's like two bodies passing in the night, and at one time they were actually closer, but they kind of passed, and now it looks like they're going away from one another?
Nah, as we have figured it out, it looks like everything came from some really small initial, unbelievably dense place and expanded from it.
Denser than my thinking.
Yeah. So-called Big Bang, which is a terrible name.
Yeah, it's not a bag.
Because first off, there was no bang. And secondly, it wasn't very big. It was about the size of an atom. But the beginning of the universe, the Big Bang was Fred Hoyle said it when he was trying to say that that was a silly idea.
Yeah.
And he was trying to make it sound really ridiculous by calling it a Big Bang.
Yeah.
Unfortunately, he caught.
And just like a black hole isn't a hole, so.
Yeah.
Okay.
Whenever I pick you down, Mrs. Brown, and things seem hard or tough, and 900 miles an hour. It's orbiting at 90 miles a second, so it's reckoned. A sun that is the source of all our power. The sun that you and me, all the stars that we can see, are moving at 1,000,000 miles a day. In an outer spiral of 40,000 miles an hour, of the galaxy we call the Milky Way. Our galaxy itself contains 100 billion stars. It's 100,000 light years side to side. It bulges in the middle, 16,000 light years thick, but out by us it's just 3,000 light years wide. We're 30,000 light years from galactic central point. We go round every 200 million years. And our galaxy is only one of millions of billions in this amazing and expanding universe. Expanding, it expanding in all of the directions it can whiz. As fast as it can go, the speed of light, you know, 12 million miles a minute, and that's the fastest speed there is. So remember when you're feeling very small and insecure, how amazingly unlikely is your birth. And pray that there's intelligent life somewhere out in space, 'cause there's bugger all down here on Earth.
Anybody that doesn't recognize it, that's Monty Python.
Yeah.
Don't forget.
It's kind of fun. It was pretty accurate, but it's about.
Remember which movie that's from? Ed? Which movie was that from? You remember?
Is that like
Meaning of Life.
Meaning of Life?
Yeah.
Life of Brian?
Life of Brian?
Yeah.
Life of Brian? Meaning of Life. This is Meaning of Life.
Yeah, I can't remember if it's Meaning of Life or Life of Brian.
Yeah, it was pretty good. I mean, the premise was he was trying to convince this woman that she really should give a live organ, become a live organ donor.
Oh,
Yeah.
that was funny.
But that's Monty Python.
We're going to never.
Okay. Now here's a summary of the whole thing.
Yes, and you too.
Yeah, kind of like that.
Yeah, it's a nice one.
Oh, wait, that's more than 415 is a, or 1415 is a channel on YouTube. They have a lot of nice stuff like that. One more thing. In the 1980s, Carl Sagan convinced NASA to turn the cameras on the Voyager back to look at Earth as it was leaving the solar system. The 1990, this picture was taken. That little dot there is the Earth. And of course, Carl Sagan had something to say about it.
No, I said, it's like this. Yeah, I said 205 because that's my professor's office. I'm not trying to get in, I'm just trying to cut it. Yeah. Sorry about that.
Playing.
It's not playing?
From this distant vantage point,
There you go.
the Earth might not seem of any particular interest. But for us, it's different. Consider again that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust, suspended in a sunbeam. The Earth is a very small stage in a vast cosmic arena. Think of the rivers of blood spilled by all those generals and emperors, so that in glory and triumph they can become the momentary masters of a fraction of a dot. Think of the endless cruelties visited by the inhabitants of one corner of this pixel on the scarcely distinguishable inhabitants of some other corner. How frequent their misunderstandings, how eager they are to kill one another, how fervent their hatreds. Our posturings, our imagined self-importance, the delusion that we have some privileged position in the universe, are challenged by this point of pale light. Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. The Earth is the only world known so far to harbor life. There is nowhere else, at least in the near future, to which our species could migrate. Visit? Yes. Settle? Not yet. Like it or not, for the moment, the Earth is where we make our stand. It has been said that astronomy is a humbling and character-building experience. There is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known.
Can't say much more about Carl Sagan. It was Big Ten. By the way, that's a picture of Saturn and the Earth. Taken from Saturn. There's Earth. Just in case we're filming data. Okay, that's about what I have.
Thank you.